Okay, so now, before we even do this, why don't we just look at the review? Because I don't think we looked at our review yet, and that's looking at these summaries at the end of the chapters is very helpful. So let's look at this one on page 184. And this is the summary of logistic regression. So logistic regression is used to predict a binary response. That's a 0-1 outcome. So basically the answer to a yes-no question. If you can't frame it as a yes-no question, you can't do logistic regression on it. Okay? And the predictor variables can be either quantitative or categorical, but the answer to the question is yes-no, binary. And then it has these three equivalent forms, right? And the S-shaped curved, and know these forms, the probability, the odds, and the log odds. And this is the one that we make regression estimates on because it's a line. So we make regression estimates for all these parameters here. Now, a useful, but this is in the log odds, and the odds ratio is e to these slopes. And that's a very useful, more intuitive interpretation of these slopes. It says the change in odds for 1 unit change in x, if you keep all the other variables, all the other x variables the same. Now for large N, we said that for large N, the hypothesis test, the significance test for the overall model, for the collective effect of all the x's, is a chi-square test. And the degrees of freedom is equal to the number of parameters, the number of betas in the model, minus 1. Okay? Number of parameters minus 1 in the log odds equation. So, for example, if it had 2 predictor variables, it would be 1, 2, 3 minus 1, 2. It's the number of x's in the model. All right? And that's the same as before. Now, and then then once we see significance for the overall collective effect of all the x's together, we can ask, okay, if we reject that, if we see significance, that means we get a small p-value, less than a cutoff point, usually 5%, and we say, okay, there's something in our model. And that means that at least one of these, let's say we had a whole lot of them, at least one of these up to kx, x's here, is significant. That's all it means. So then we want to test these. And we have, and then we use a z-test. And the confidence intervals for the slope are built using the normal curve in the log, which means we then have to transform them by exponentiating that confidence intervals. And if we want to get the confidence interval for the odds, and then we get those asymmetrical ones. Now, for not so large n, usually what you're used to is for not so large, we'd use either a t-test here for the z or a f-test, but you never do that with logistic regression because remember, these are counts. So the mean, if I tell you, if you have a count, and I tell you like we have, I don't know, 40% ones, we're counting by ones, you have 40%, you know that what the standard deviation is. Whereas if I tell you the mean when we use quantitative data and aren't just counts, when we use continuous, we have a quantitative y, if I told you the mean was 50, you'd have no idea what the standard deviation is. And that's why we use these t and f distributions when we have an unknown standard deviation. We never have an unknown standard deviation. It's tied to the mean. So, but that doesn't mean that we can use, for small n, we can use, we use very similar methods using likelihood calculations. We just use similar methods if it's really small that in the long run approach the chi-square and the z. They're very close to them, but they're slightly different. Okay? And the other thing is, you remember the whole beginning of this chapter, we looked at violations of assumptions. And we did these transformations, those log and square root transformations, when there are violations of the assumptions. With logistic regression, that's because we were using least squares estimation. Now, we're always using maximum likelihood methods instead of least squares, so there's no assumptions about the normality of the residuals. That was a big one, the normality of the residuals, right? Like there are for T and F tests. You should still check whether the log odds is the best fit, best linear fit. Like once you get into the log odds, you have to see if it's still the best linear function of the predictor variables rather than some other function. There might be some other thing we have to use, but we don't check the residuals in the way that you do for all the other linear models because we're not looking at least squares estimations. So we don't have to have normality of the errors. We won't have normality of the errors. Okay, so that's the idea. Now, let's go and do the problems. Okay. So I'm just doing the yellow practice exam here. I just thought it might show up better. Maybe it doesn't, but we'll see. Here. Okay, so now first off it says, here's some of our data. And it says, when you graduate, are you more interested in doing good, helping others, or doing well, gaining material resources? On a scale of 0 to 10, where do you fall? Meaning you can't, So you answered these questions. And then we also said, what is your expected income 20 years down the road, adjusted for inflation, like if it was in today's dollars, and you answered, and this is in thousands. And so I was interested in correlating those two. How much whether you care about, doing good or well correlates with how much money you expect to make. And when I tried to plot it, it looked terrible. And here, maybe it looks better here. You can't even see it. Maybe you can see it better here. Okay, it doesn't look good. So I want to do a transformation. Look at the errors around here. They're all above, and there's all squashed down here. So I say, what's the question? Look at how the y values, the expected income, are all squashed at the bottom of the graph. And so I said, okay, I want to do a transformation. So I looked at the y variable here. The y variable is income. And look how enormously skewed it is. Like, it's so right skewed because some of you are answering astronomical amounts of money like that. And so you can't even see the people who are giving reasonable, we can't even see what's in there. So what transformation do we want? What do we want to do? We want to bring these extreme values, basically use their exponent instead of the values. So, change it to a scale between, to a much smaller scale. Well, I'm giving away the answer. How do we, if we have right skewed data like that, what do we want to do? Well, the question says circle all that could not work. Well, these are going to make bigger values even more extreme. So y squared, y cubed, and e to the y. These are ones that will not work. These all are for left skewed data. So these are for left skewed data. And we have right here, we have, this is right skewed. So we have a long right-hand tail is right skewed. See, it goes way up. And just all income looks like that because it's cut off at 0 and it just can go, especially expected income, how much you hope to make. Okay, so when we have long right-hand tail, you want to use what? The square root would bring those in, the square root of y. If that doesn't work, the x, if you take the log and use the exponent, that's more extreme. And then finally, and we haven't really done this, the 1 over y, which is going to make the biggest values turn into the smallest values, but it flips the direction, so it's not often used. So these are the two that you'll usually see, and those are the two that will be usually on the exam when we actually do transformations. So these are the ones we want to use, but it said right here, not work. So you just got to read the question carefully. Okay, so that's the answer. Now, here's the transformed expected income. So which of these do the histograms depict? Well, you can see it helps somewhat. We can now somewhat see, looks a little bit better. And you can see the numbers become, but so this must be the square root, and this must be the log, the next one. All right. It's still skewed here, so that's why this is still skewed. So that's why we want to go further. It's still skewed here. All right. So I'm trying to have this make sense. So like lots of times the cues are in the data itself because it's real data, and I want you to look at real data. Yeah. Yeah, no, I meant to thank you. Thank you so much. Yeah, and you could do that on the test, and sorry, you lose points. Sorry. I'm very sympathetic to that, but there's nothing I can do. Yeah? Could I explain why? Well, you know that these three options aren't good. And you know that this would even flip the direction. The biggest, so you know it can't be that. So between these two, why is it more extreme? Well, just think of, like let's look at 0 and 100. If you took the square root of those, right, you get, if you took the square root of 100, that would bring it to what, 10. But if you took the log, or the log base 10 of 100, that would bring it all the way to 2. It brings it down further. Right? Well, and that's even more true the bigger you get. Like a million has 6 zeros, so it would bring it down to 6. Whereas the square root of, so this one brought it further. It was still skewed here. It's a good question. It's still skewed, so we want to, see how the numbers are much bigger here, and the numbers are smaller here? It's still skewed. We want to bring it down further, and so that's why we go all the way to the log. We're talking about the y-axis. This is the y-axis. This is expected income. It's on the y. The y is, you do it, you remember you start usually with the y-axis? We're just looking at the y-axis here. This histogram's of the y-axis. I started here. This is a scatter plot. And then I said, okay, these variables, like we have to make a transformation of either the y's or the x's. So there's lots of times lots of x's, so one y. So why don't we just start with the y and transform that? So we start with the y, which is expected income. So this is a histogram of the expected income. And if we transform this, I know that this is not going to be needed to be transformed. It's just on a scale of 1 to 10. It's not going to be very skewed either. So now I'm just looking at the y's. Does that help? Good question. I mean, I'd like you to ask questions like what's going on. Yeah?
So the histogram on the left is not accompanied by the histogram on the right? Do you have any way of determining whether it's true or why?
Yeah, you could, because you could just like take the square root of these numbers and see they kind of match up. It's another way of doing it. All we're doing is taking the square root of these numbers or the logs of these, natural logs of these. So you could just do that as well. Usually there's lots of different ways to do a problem. I provide, there's not just one way to look at it. There's lots. This is just sort of, if I didn't provide you with that axis, if you didn't see the numbers, then it would be hard. Does that make sense? Any other questions? Okay, so let's go on then. And so now below is the scatter plot now of the transformed variables. You know what? I just want to emphasize that you're probably like, some of you are wondering, wait a sec, because we're not doing logistic regression here. We're doing ordinary regression. We're just changing the y variable. So even though it's log here, it's not logistic regression. So this is much simpler. It's what we did in the beginning. So now all we've done is transform the y variables, logged them. And now we're looking at the same rating on a scale of 0 to 10. Where do you fall? And now we're, instead of looking at the expected income, where all these things were bunched down here. Here you can see how they're all bunched around 0. It looks like we can't even see it. It's like those little animals that were all squished together. We can't even see. We want to count these people just as much as the ones who said a lot, but we can't see them. So when we take the log, they become visible. And now we can actually see, at least in the log, we can see the responses. And we can actually do a nice prediction here a linear equation. This one's the residual plot. I'm just showing you how nice the residuals are too. And here we want them to be normally distributed. We're not doing logistic regression. We're not predicting zeros and ones. We're predicting a quantitative variable. So this whole, all the ordinary, we want normally distributed errors, and we have them. See how they're like all bunched around the average here? And they look like little normal curves if you made histograms of them. So this looks very nice. And so now, use the above equation to estimate the log expected income. All right, so now we've got this equation here, linear, in log. It's equal to an intercept plus a slope times the rating. So that's really easy. We just say for 5. So we just plug 5 in for the rating there. I just want to know what to predict for somebody who's right in the middle. How much did they expect, or somebody who's dead center? So it's the predicted log of the income is 4.3, that's all I'm asking for, times 5, 0.11 times 5. And thank you. And that is equal to 4.85 as a log. But so how much money do they want? You can say their log expected income is that, but now we just want to know how many dollars is that. So we just anti-log it, exponentiate that, and then we get the number of 100. I got 127.74 in thousands. So that's 127,000. We couldn't even see that before, but now we can see that. That just looked like 0 up there. Okay. So now we want to compute a confidence interval for your estimate in part 2. So read it carefully. A confidence interval around that. Well, we can't do that directly. Why? Because what are we going to use for our confidence interval? This standard deviation, and that is associated with the log. So be careful here. So we're using this to, how many of those? 95%, and they say use 2, so 2 of those added to this right here, right? Added to the 4.85. Not to that, to that. Okay, so our prediction. Here's our point estimate. We want to give some wiggle room. In the wiggle room, we want to be 95% sure. So this is like we want a 95% confidence interval, margin of error there. So that for the log, so we'll say 95% confidence interval for our prediction, which is associated for the log of the expected income. It's not real intuitive, but that's for the log of that, is equal to, that's our point estimate, and our margin of error, just our wiggle room for 95%, is plus or minus 2 times our standard deviation there, of the errors around our prediction. So that's plus or minus 2.6, all right? And then, but that's not what the question asks. It asks for dollars, not exponents, for the dollars. So now we just have to exponentiate it. So the 95% confidence interval, and this is what we do again for logistic regression, this type of thing. And for the expected income in dollars, not the log of it, but the expected income, so this is dollars here, is equal to e to that whole thing. So we're just going to say e to the 4.85 minus 2.6. We'll go there. I can write it. So this is e to the 4.85 minus 2.86. And the upper limit will be e to the 4.85 plus 2.86. No, not 2.86, 2.6. So sorry. 2 times 1.3. 2.6. All right, so we do that, and I did that, and I got 9.49 to 1719.86 thousand, and you notice it's an asymmetrical confidence interval. This is not the average of those two. If I wanted to check it, what would I do? I'll just do the check down here. If I wanted to check it, do you see what I do? I just take the square root of those two things. So the way I wrote it makes it super easy to see why that would work. You would take the square root of e to the 4.85 minus 2.6 and e to the 4.85 plus 2.86, and those cancel out. And that's why you get, when you take the square root of that, you're just going to get e to the 4.85, which is that. So you can just say, so the square root of 9.49 times 1719.86, and check and make sure it is e to the 4.85. And it is. I didn't ask you to check it, but I'm doing this because it's a lead into this one. I said, what if you just had the confidence interval and I asked you for what the prediction is? You can't just take the average of those two things. A 95% confidence interval for the expected income of another student is that, right? Another student is that. It's smaller, so he must have given an answer smaller than that. I mean, this is smaller than that. I mean, it's lower. This is lower than that, and that's lower than that. But what is it? Well, you can just use, if you take the geometric mean instead of the arithmetic mean, it's called the geometric mean, you'll get the answer. And I got 73.67. So that's what goes in here. The problem above is the answer is this. Did I square root the wrong numbers? Where? Here? The answer to part... Oh, damn. Sorry. I'm just doing the same exact problem again. Duh. Sorry. Yeah. So annoying. I mean, these are... Yeah, now you get one answer, now you get the other. I am so sorry. This, you know what the problem is? These print... You see, our notebook's 12 point. I honestly can't read this, even with glasses, so I'm trying to remember a lot of what's on here. I mean, I can barely see this because I wanted to print it out bigger, but I don't know. Anyway, it's very hard for me to read these. So, if I was taking this exam, I'd have to take it at Dres for vision problems. Okay, or else have a bigger copy. So this is, now I can see it. I mean, I can see it, but it's very hard for me. So these, of course, this is this one. And thank you so much for helping me out here. Okay? So, and that is 73.67. All right. So far, I'm getting about a B on this exam, right? If they give me partial credit. All right, let's turn the page. All right. Ooh, these are kind of, I don't even like this question very much because it's kind of confusing. Each plot will be the answer to exactly one of the questions. So that means that you're going to use, you're not going to use these exactly one of the questions. So after you use one, just cross it off. It won't be the answer to another one. Let's start off. Which plots are well suited, and I have plotter plots, it's just confusing. I'm sorry about this. I don't like this question. Which plots are well suited to linear regression as they are? Well, this one certainly is. E. So that means we're not going to use E for anything else. Are any of the others? Because we could use another one for it. I don't think so. Doesn't look like it. This one has kind of a curvature here. This one has that fan shape. This one has these two groups. This one certainly is curved. And this one has another two groups. Okay, so none of them are well suited as they are. Okay, now which ones show a curvy linear trend? Well, certainly that one. So we're not going to use it again. And that one too, I would say, because that does. So we won't use that one again. Now let's see, which plots should be broken into subgroups since they show two distinct groups? Okay, so those are two, that's an easy one, A and C. We're not going to use those anymore. And which plots are linear? We're not using this one either, so it has to be this. Which plots are linear but would not be suited to using the standard deviation errors for building confidence intervals? Well, this wouldn't at all, because look how big the errors, if we made it, this is linear, but there's so many, the range of the errors is so much bigger here than here, the spread of the errors. So it's D. So that's our answers. All right. Now, this is easier to read if I look up there. Okay, so why don't you just take a minute and make sure you can answer these right. People had problems with this first one. That's what I remember. For which of the following would be appropriate to use either simple or multiple logistic regression? Remember, can you change these what you're predicting, the y variable, into a yes or no question? This is predicting whether you get either. What I wanted to say is either an A, a B, or a C. Like there's three groups here. That's what I meant to say. Okay? So just now see if you can fill these out. I think it's better if I said predicting whether you get either an A, a B, or a C. So it's three groups there. All right, so this one is no because there's three categories. So the answer is no. This would be an ANOVA problem, right? Or compare the means of the hours studying for people who got an A, compare their mean to the people who got a B and a C. It would be, this is a classic ANOVA problem. Okay, this, predicting whether you get an A on a test from hours of studying, yes or no? Did you get an A or not? Whether or not, yes. That's predicting surviving breast cancer, survival or not? Yes or no? Did they survive or not? So this is yes as well. Years of survival, you'd answer with a number. So that's no, you just do ordinary regression. And predicting the log of the income. Just because it has a log, that doesn't mean it's logistic regression. That's a quantitative variable, so that's no. And the x's can be either quantitative or categorical. All right, now, so what you just check whether the y's are, just check whether the y's are 0, 1 variables. Yes, no questions. Binary. Now this is really easy. I don't think I need to go over it because people, it's so, I think that you've done this a lot, and probably people have suggested to me that I don't do a chart on, that's good for homework, but I probably shouldn't do it on the, make it somewhat more challenging. And just so you probably won't see this whole chart because you have a bunch of, people who came before you didn't have as many practice exams. So now that you have practice exams with charts like this and you've had a homework, it's pretty easy to fill this in. So how about if I just gave you, like, for example, just said, just one of them, like, I don't know, something like, you could do it, like, you should be able to do it, something like the log odds, I don't know, just make up a number, is equal to, I don't know, negative 0.5. So what's the probability? So P is equal to what? Something like that. 1 for each one, or the P is equal to something, or 1 minus P is equal. And then you'd have to think of this on your own. So for example, here you'd know what? The log odds, you have to get from here to here, you have to go through the odds. So then you would have to say, then you'd just exponentiate it. So you'd write that would be your work. The odds is equal to e to the negative 0.5, and then the probability is equal to e to the negative 0.5 over 1 plus e to the negative 0.5. Right? because the probability, what I want you to know is, probability is equal to odds over 1 plus the odds. You could write it out and make the chart yourself. Just go, right? So if I said odds are equal to 0.2, then you'd know what? You would say, then you just take the log of 0.2 to get the log odds, if I'd asked you that. And then, what would you do here? What would the probability be? 0.2 over 1.2. Right? Odds over 1 plus. You can just always do this. That helps you. And let's say I said the probability is, or maybe I could say, I don't know, I could do like, what if I said 1 minus p is equal to, 0.6. I'm just making these up. Then how would you get the rest of these? What would be the odds? Remember, it's p over 1 minus p. So that would be in the denominator. And in the numerator would be 0.4. And then you just take the log odds of that. 2/3, etc. I don't think I'm going to give you a chart, is what I'm saying. Because everybody can just do these charts without even, you know what I mean? It's good for homework, but I think just because the grades are so unbelievably high in this class right now, you don't want to just get an A when everybody else is getting an A, right? That won't make you feel special. Okay, but I'm telling you, if you can do, also, you should be able to go back and forth between them, right? And you can always make the chart. Just say P odds, log odds. You have to to get from here to here, you go through the odds. All right, now, I love charts, but I think they're better for learning, and maybe on the test I should make sure you know how to do it. Same with this one. Look, I gave you the whole chart here. So if I ask the probability, you first do that. You should do that on your own. I'm going to ask you for probably the probabilities here without giving you the whole chart. All right. Now, so on our last survey, this was a while, it says, students answered 3 questions. Would you date someone who's transgender? How many children would you like to have? And are you male or female? And so here's the output. Suppose they were randomly chosen from all 40,000 UI undergrads, and here's the output. Okay, so here's our logistic. So what this output is for is for the log odds. So we have this equation right here. The output is, this is very easy, this part, negative 1.604, these coefficients, plus, tell me if I miscopy anything, please. Okay. I know I skipped these. I just wanted to show you what the equation looks like. All right. Now, the question says, and how are males coded? Males are usually coded, we keep it consistent, we're always coding them as 0 and females as 1. All right. Now, are males more or less likely than females to date a transgender, given that they have the same number of children? So for the same number of children, you're just looking at this coefficient, right? And it's positive. So as you go from x is equal to 0 to x is equal to 1, from male to female, it says females are more likely to date. So males are less likely. If it was negative, males would be more likely, because look at the way they're coded. Does everybody understand? This says as you go from 0 to 1, this is the change. Gender can only be either 0 or 1. So for female, there's a higher predicted log odds, which means higher probability. Now, the more children desired, you have a negative here. So the more, it's negatively correlated with dating a transgender. So the more children desire, the lower, because there's a negative correlation there. there's a negative correlation between males and dating a transgender too. I mean, males are less likely. All right, what's the estimated odds ratio for gender? You should all know this. Odds ratio is just e to the slope for gender. If it's for here, e to gender, so e to the 1.022. That's the odds ratio. And this one for children is e to the negative 0.3823. So this one is greater. This is than what? 2.72, and this one's less than 1. All right. Now, I don't have to fill this out for you. This is just plugging in a 0 into this equation for gender and solving it. And then what would you do? Then to get the odds, you'd say e to whatever you got here, e to the log odds. And then the probability is just whatever you got here, that's equal to odds over 1 plus odds. So I'm not going to go through that. You can do that on your own. You had no problem on the homework with that. That's just plugging and chugging. And that's why I think I'm going to not do the whole chart, but just have you predict probabilities and so forth for different, so you can do that on your own. So practice that and make sure you know how, the chart's not there. All right, now let's look down here. Kate wants 3 more children than Sarah, so compare their odds of dating a transgender. How the odds change, the odds ratio, okay? The ratio of their odds. So that we have to use the odds ratio for children here, because we're talking about children, 3 more children. So we're using the odds ratio for children. And that's equal, we just did it. All right, so that's the multiplicative change for each one increase in x for children. So it's multiplying 0.68 times 0.68 times 0.68. That's your answer. Same as this times 3 up here. All right, so that's the answer here. Now, compare their probability of dating a transgender. Well, that changes. An increase of 3 is going to be different. Remember the curve we're talking about? We have to know where they are on this curve for probability. This is our probability curve. And it doesn't change by the same amount, either additively or multiplicatively. Look, it's really gradual. It's going to be a big difference right in the middle here. When we in the sort of like the average number of children, like maybe, but if there's not going to be a big difference when you go from like 6 to 9 children, or up here or down here. So we can't answer it. We do not have enough. We need to know x. So we need to know where along here. Need to know the x variable, which is children, number of children. Or the odds themselves, not the ratio. Because if you know the odds, well then you know the probabilities. But we don't know the odds, we just know the comparison between their odds, the ratio. All right, the odds of a female dating a transgender are the same as the odds of a male. When what? So we're looking at this equation here and we're saying, okay, when these basically are the same here, like when gender, okay, you get the female is more likely to date here, but the more children she wants, the less likely. So when would they equal out? So just set them equal for male and female. So just set this equation for males and females equal, and then solve for the children men want compared to the number of children female want to make them equal. All right, so let's just do that. So for men, we have what? Negative 1.604 plus, I'm plugging in as 1.002 times gender is 0 for men. I'll just do 1 for females. Okay, I'll do the females first. Okay, and then I'll say minus 0.3823 times the number of children for the females. So that's the females. And then for the males, I'll do the same thing. I don't really have to do it because they're on both sides, right? And I don't have to put in anything, but I'll put it in anyways. That's times 0. I don't need that. Minus 0.3823 times the number of children for the males. All right. So these cancel out, these cancel out. And I'm left with 1.002 is equal to, bring that to the other side, 3.823 times the number of children for females minus 0.3823 times the number of children for males. Okay, so we'll just divide both sides by 3.823. So we get, that's the difference right there. And look what I did. Gosh, I'm so sorry, I miscopied that. That's 0. Right. Okay. So it's 0.3823. That is, there's no decimal place there. All right. So we have 1 over 0.3. Right? So our answer is just whatever that is. And so that's equal to 1.002. I'll just make it more clear, and I'm sorry I'm making it messy. 0.3823, which is equal to 2.62. Okay. Sorry, all these decimal places. It's just because we're using this real data. I should round it for you guys. Any questions on that? All right. Now, what are we doing? A fourth question asks, are you a U.S. citizen? Yes or no? This is all real data. I'm so curious. How is that correlated? So U.S., if you're a U.S. citizen, you're more likely to date a transgender than if you're not. All right. And here's the output. So a chi-square test was done for the overall regression. We have a huge sample size. Now, if the sample size were smaller, would it have been appropriate to do an F-test instead? Absolutely not. No. We wouldn't. We'd have to do some adjusted, like chi-square, some likelihood thing. Never an F. It makes no sense to do an F or a T here. How many degrees of freedom for the chi-square test? What? Your question is something I can't hear. Is it no because what? Yes. It's no because actually, excellent question. We should make sure you know this. So also, where did I put it here? Turn to page 181, not just in the summary, but on page 181, right here. In logistic regression, we're predicting counts, so we never use F-test. And here's where it's explained. And here's where the degrees of freedom are explained, right here. And for the individual slopes, we never use the t-tests. And it is explained why here. So this is a better explanation than in the summary. So I'm glad you alerted me to that. This is a good page. Time, to read. All right. So the answer is no. And So let's answer no to this one too. If the sample size were smaller, would it have been appropriate to do a t-test for the slope instead of a z-test for the individual slopes? No. Now, how many degrees of freedom for the chi-square test? Well, how many parameters do we have here? We have a beta 0, a beta 1, 2, and 3. We have 4 parameters, so these are the number of parameters. So it's going to be, remember, the degrees of freedom is equal to the number of parameters minus 1. We have 4 things we're estimating. These are parameters we're estimating. So it's 4 minus 1. All right? Now, calculate the z-test. You should all know how to do this. It's the observed slope for citizen right here, the one that's blank. So the observed slope minus the expected, which is 0, that's under the null, over the standard error, which is given to you. So that's a really easy problem right there. And I got, when I did that, 3.17. So that goes right in here. And the p-value is missed. Is the p-value less than 5%? Do we even have to look that up? Do we? These are for the individual slopes. You know that 3 sigma, 3 is going to be significant. Don't you all know that? I mean, 2 sigma, 2 standard deviations, has 2.5% on either side. This is much bigger. You don't even have to look it up. Yes. Go ahead. Yes. You'll be given one if you need it. I think I wanted to save paper, which is why I didn't do. Because I thought you all know how to do that anyway. All right. So did I put one on here? No. So you might have one, you might not. You'll definitely have it on the final. Okay, now to test where the individual slopes are significant, the program does 2-sided z-test. Here, what does that mean? It means that our null is always that the slope is 0, but the alternative is that it's not equal to 0, instead of saying it's greater than or less than. So how would the p-values change if we did 1-sided tests? So you should know this 2-sided, this is very easy. 2-sided means you don't know which side it's falling on, so whatever p-value you get, it's saying, it's counting as if it fell as extreme in the other direction. That's your 2-sided. So that's what these p-values are. This is your p-value. Now, if you just know ahead of time, say, hey, I know it's going to go fall in there, you don't have to do that one. So it's half of it, right? The 1-sided is just 1, 2-sided is 2. So this should be very easy. They'd be halved. And that's why people like you to do 2-sided, because they're more conservative. They feel like, hey, you really didn't know ahead of time. You looked. Now you're going to make your p-value half as small so you can get published. Well, screw you. We're not going to let you do that. And that's why all the programs, they all want to do the 2-sided, just because they don't trust people politically. Motivated. I mean, not always, but that's pretty much why. Okay? Because you get smaller p-values with 1-sided. Now, compute a 95% confidence interval for the gender slope. So I'm saying you may use z equals 2 just to make it easier to grade. To go with that. So that is a super easy problem. We just take, where is the gender slope? Biggest problem is people just read this table wrong, and I'm almost doing that. We're talking about these slopes right here. This one's the gender, so this is the one we're looking at. So 0.9997 plus or minus, now they told us to use 2, and here's the standard error associated. Let's just not make a careless error. And that is it. So we're going to subtract 2 times that from that, and I got that when I did it, and add, rounded to 2 decimals. And 0.997 is right in the center of that. As you can see, we're adding, subtracting the same thing. The average of that But now we want to compute a 95% confidence for the odds ratio. So, in the odds ratio, did you even compute what the odds ratio is here? No, but it would be E to that. And a 95% confidence interval is just going to be E to that. Just exponentiate that. I got 1.86 to 3.97. You could check that by taking the square root of, taking the geometric mean and making sure what? That it is e to the 0.997. All right, now, in general, if a two-sided p-value is less than 5%, okay. A 95, if a two-sided is less than 5%, what do we say? And yeah, the two-sided p-value for the slope in the log odds equation, so these p-values right here are less than 5%. We're testing, what are we testing? We're testing whether it's 0 or not. The slopes are 0 or not. And so we're saying if it's less two-sided, that means we got some slope that's, when we convert it to z-scores, that's between 2 and -2 here, but, just some slope that's in this range, right? Where this is 2.5% and that's 2.5%. And it's less than that, so it's somewhere in here. And what's the question then say? So 95% is in the middle. So if we got significance, that means we're either here or here. And what does that mean? That a 95% confidence interval for the slope doesn't, we're here or here, so it doesn't include 0, right? But then when we change it to the odds ratio, that's the same thing as saying what? Well, log odds equal to 0 means the odds are equal to 1. So that means that it does not include 1. It's the same thing. That you're not favoring one, that going, an increase in x is just equal odds. Like 50-50 probability, equal odds. Those are all the same thing as in log odds of 0. So now let's go to the next page. And these are just looking at these graphs here. And right away, you should be able, okay, so let's say we're predicting acceptance to medical school based on the MCAT scores. All the grades below depict MCAT on the x-axis. And y-axis is either probability odds or log odds to acceptance to med school. Which is which? Well, right away, you should know this S-shaped curve that's bounded here and here. 0 and 1 is the probability. So this is the probability curve. And this is the log odds. It's just a line. And it goes from -infinity to +infinity. And in between here is the odds are always positive. They're p over 1 minus p. But they go from 0 to +infinity. So there we have it. All right. So plot B, A, and C. All right. Now the equation for, this one right here. You should know that one as what? Odds over 1 plus odds. That is this S-shaped curve. This is the probability. Right? It can never get bigger than 1. And can never be negative. This is your probability. And this is the exponential curve here. The smallest, it's the limit, it goes from 0 to infinity. And this is your odds. Okay? Now, judging from the plots, what MCAT score gives a 50-50 chance of getting into med school. So what score? So here's your 50-50 line, 0.5 probability, and what is that? Boy, I can't even read it, but it's right there. Oh, sorry. Whatever that is. 510. All right, so that's 510. Let's go out again. The score that gives a 50-50 chance of getting accepted has a y value of what in the other plots? Well, you can do that, right? So the y value, just a probability of 0.5 is the same as odds 1 to 1. So we can look on this one. That's my odds of 1. This one's kind of easier to read. That's 510. They should all agree. And a log odds of 0. Oh, that's the easiest to read. So that, and that. They all agree. Okay. Has a y value here of plot A is 5. The y value, not the x. Okay, so that's pretty much it, and it's such a gorgeous day, and I think you know what to do. You have a practice exams online I posted. You have one on Lon Kappa, and you can also, I'll put all the homework on again. I'll look through the homework and maybe I don't know, I haven't written the exam yet. So I'll put all the homework up, and there'll be office hours when? Tomorrow and Monday I'll have them 2 to 4.